backwards. Now we're aware of time because we notice that things happen one after another in sequence. We've got lots of ways of measuring time. We have sundials, watches, and clocks, and they're natural clocks too. Like we sleep at night, bees buzz during the day, and trees lose their leaves in the fall. Now all the ways that we measure time are based on how fast the Earth goes around the sun. Take a look at this. It's our Earth, Sun, Moon, time-keeping motion machine of science. Now here's the Earth out in space. It goes around the sun in this direction. Now for the Earth to get all the way around the sun, back to where it started, takes 1 year. So every year we have New Year's Day.
Happy New Year!
There's your birthday. That's my mom's birthday. And there are all the other important holidays and events that we mark on a calendar. And that takes 1 year. Now at the same time the Earth is going around the sun, the moon is going around the Earth. For the moon to get all the way around the Earth takes a month. In fact, the word moon and month come from the same word. Meanwhile, the Earth is spinning on its axis.
The Earth is always turning, once every 24 hours. The center upon which the Earth turns is called its axis. The axis is an imaginary line through the Earth from the North Pole to the South Pole.
So for the Earth to get all the way around the sun, we call that a year. For the moon to get around the Earth, we call that a month. And for the Earth to get all the way around, we call that a day. Now, it took our ancestors thousands of trips around the sun, thousands of years, to figure out how much time it takes for all of these things to happen. When you know how long it takes, you can figure out when to plant your crops, who won a race. It's like we live on a big clock. If you watch shadows during the day, they move. When the shadows are the shortest, that's the time we call noon. Right now, it's morning on the east coast of the United States. But as the Earth turns, the shadow turns with it. And pretty soon, the shadow is the shortest. It's noon over here. But look, on the west coast in Seattle, the shadows are very long. It's morning. We have to wait for the Earth to turn all the way over here for the shadow to be the shortest. Now it's noon on the west coast. Everywhere along the Earth's surface, it's noon at a different moment. For centuries, we've divided a day into 24 hours. So now we divide the world into 24 time zones. Each time zone is 1 hour wide. And although the sun isn't directly overhead at noon, everywhere in the time zone, everywhere along the Earth's surface, it's noon at a different moment. We've agreed to set our clocks and watches to the same time in each zone. Each time zone is 1 hour wide, and each zone is 1 hour different from the zone next to it. So the world goes around once a day in 24 hours. So now we have 24 time zones around the world. Hey, Alan, what are you doing?
Hi, Bill. I'm just trying to figure out what day it is.
It's Wednesday.
Yeah, it's Wednesday here, but it's not Wednesday in New Caledonia.
Oh, because it's across the international date line.
Right. It's the line where we start counting time zones, and it's only on one side of the Earth. You know, it's like the start and the finish line on a racetrack.
Yeah. Because if you start here and you go east, well then you know every what? 15 degrees, you get another hour. Eventually you'd get to where it was later. It was later and later and later, and then of course you'd say to yourself, well, it's late enough to be the next day. I'm after midnight. They're somewhere in some other time zone here. And so then that wouldn't make sense. Please, it would be earlier, like on the same day.
Please go
away. Catching up with the old day. Like that. It wouldn't work. So then what they did, they had to draw the line somewhere. They drew the line right there. That's the one right there, the international date line. That's it. That is a cool idea.
Bill, do you know where the science guy jumped out of a plane wearing his watch?
No.
Well, could you go find out?
Here is a totally cool clock that you can do at home. Take 3 paper cups and you poke a hole in the bottom of each one. Then you use thumbtacks to hang them on a wall, one above the other, like this. You need a big glass jar at the bottom here. Now you fill the top cup with water and you start a stopwatch at the same time. Exact same time, ready, go. Okay, after 5 minutes, you make a mark on the glass jar at the water level. You do the same thing for 10 minutes and you keep marking the jar. See, now you got a water clock in 5-minute increments. You don't need a stopwatch anymore. You can time anything you want just by using water. Try it, okay?
We're gonna go back, way back. Back before people had digital watches or computers to tell time. Back then, we relied on the sun.
And they measured time with sundials. As the Earth turns, the shadow turns with it. Sundials were the first clocks to keep track of hours. Now, if you watch the shadow on a sundial, it goes this way when viewed from any part of the northern half of the Earth, the northern hemisphere. That's why our clocks go this way too. They run clockwise because of the shadow.
The 2-minute warning has just been announced.
That means there are count them, 2 minutes left in the game.
2-minute warning is sponsored by Nanoseconds. Nanoseconds, there's a billion of them in every second.
And by the International Dateline. Looking to go back a day? Just cross over the International Dateline.
Astronomers start the year when a group of stars is directly over an observatory in England, when the day and night are the same length, what we call the equinox, equal night.
There is now equal night and equal daylight.
When the Earth goes around once, that's a day. When the Earth goes around the sun once, that's a year. Here we go.
Bill, how much time is this going to take?
By the time the Earth gets back to the equinox, it's turned about an extra quarter of a turn, about an extra quarter day. So after it's gone around the weather balloon, around the sun 4 times, it's turned 1, 2, 3, 4 extra quarters, or 1 extra day. That's a leap year, and we add an extra day, usually on February 29th. Here's the thing, it's not quite a quarter of a day, almost. So every 3 out of 400 years, we skip a leap year. So the year 2000, that's a leap year. The year 2100 is not a leap year. See, now nobody lives to be 400 years old.
You don't say.
But humans keep track of all that time.
Try to measure 30 seconds without looking at a clock. Have a friend time you. They'll tell you when to start, and you'll tell them when you think 30 seconds is up.
Ready, set, go.
1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi, 8 Mississippi.
This
9
exciting
Mississippi.
demonstration to be continued.
Take a look at this. Here are 2 bowling balls hung from the ceiling on wire ropes that are exactly the same length. This one is pulled back about twice as far as this one. Now watch what happens when we let them both go at the same time with these magnets. Ready? Click.
Okay, I'm watching.
See, even though this ball is swinging faster because it started higher, they both cross the middle point at exactly the same time. Even though the pendulums are pulled back different amounts, gravity affects them both exactly the same. They both have the same period. It takes them the same amount of time to swing back and forth. Even as the pendulum slows down, it still keeps the same period. That's why pendulum clocks are so accurate.
Tick by tick to the hour.
Now, this was discovered by Galileo Galilei as he watched chandeliers swing in church. He measured their periods with his pulse, and he knew how it worked. In a heartbeat. Haha, get it?
And now back to our exciting demonstration.
27 Mississippi, 28 Mississippi, 29 Mississippi, 30 Mississippi, stop.
Not bad. You counted 30 seconds, but my stopwatch only counted 25 seconds. You counted too fast. Now you can see why we invented clocks and watches. Can you imagine what it would be like if we had to count seconds, minutes, and hours all day long? Try counting off 30 seconds to yourself. How close can you get to 30 seconds on a watch? Come on, try it.
Can people in spaceships really travel through time? Well, please consider the following. You can't talk about speed without talking about time.
All right, get ready.
If someone throws you a ball from a moving truck, the speed of the truck adds to the speed of the ball. 59 miles an hour. The truck was going about 20 miles an hour. She must have thrown it 39. The speeds add up. If the truck is going away from you, the speed of the truck subtracts from the speed of the ball. "22 miles an hour. Now the truck was going 20. She must have thrown it 42 miles an hour, and they subtract 22. Light is pure energy. It's not like a ball. And scientists have measured the speed of light very accurately. And even though we're living on a planet that's spinning like crazy and circling the sun way faster than a truck, when we measure the speed of light, whether we're going this way or this way, we always get the same answer, no matter what direction we're going or how fast. The speed of light is the same. It's weird. It doesn't speed up or slow down like a ball. The speed of light remains a constant 300,000 kilometers a second.
All right, get ready again.
It's like somebody threw you a ball from a moving truck and it didn't speed up or slow down. No matter how fast the truck is going or in which direction, the light from that spotlight always goes the same speed. Now you would just not expect that. A very famous scientist named Albert Einstein got to thinking about this. And he thought that if the distance a beam of light travels stays the same, the only way for the speed of light to remain a constant is if time can change. He reasoned that the speed of time can change. Then he did a very famous, what he called, thought experiment.
Experimentally.
There are 2 twin brothers. One twin is sitting on the Earth. The other brother gets in a rocket ship and zooms off on a big space journey Now the brother in the rocket ship is traveling fast, nearly the speed of light. When this brother gets back, time will have passed more slowly for him than time for the brother on Earth.
You're looking good.
It's not just that time will seem to have slowed down. It's that time for one brother will actually have sped up or slowed down relative to the other brother. This is what Einstein called his theory of relativity.
The special theory of relativity.
Now, we've never built a rocket that can go nearly as fast as the rocket in Einstein's thought experiment. But time for astronauts does pass ever so slightly more slowly than time for us here on Earth. Near as we can tell, the theory of relativity is true. Thank you for joining me on Consider the Following.
I'm Andy Michigan, and I'm working on a project to send robots to Mars. This is a small mobile robot. We talk about them as rovers. One of the major problems we have in dealing with controlling a rover like this on another planet is the problem of time delay. If it needed to communicate back to Earth, back 50 million miles away, in order to say, here, I've got a problem, even traveling at the speed of light, that message would take 10 or 11 minutes. And then whatever we did on Earth to decide what to do would take another 10 or 11 minutes to come back. What we're seeing on the screen is really what happened 10 minutes ago. We're looking back in time at what the rover was doing 10 minutes before. So here we're driving along, and we see we're getting closer and closer to this rock. And we're saying, well, we want to turn away, but this is history. This has already happened. So the rover comes in, and look, it gets in trouble, it's hit the rock, we're in trouble, and we've got commands going to try to say, hey, turn, get away from the rock. But it hasn't heard it yet. No matter how loud we yell, it's still going to be 10 minutes before that message gets through to the rover. And it's too late. We need to make the robots more intelligent so that they can handle those problems on their own, so that we tell them what we want them to do for maybe an entire day, and then they drive around and get to the right spots and avoid the obstacles that they see. And if they can't and it's too big of a problem, then they'll call home. But otherwise, they'll drive along on their own and do experiments where we want them to do them and find out more about Mars.
Hey, it's time for science.
Is that clock ever gonna move? Time is supposed to be passing at a constant rate. I think this is the longest minute of my whole life.
Once we measure a second, it's gone. What's up with that? This picnic sandwich is 1 meter long. We can measure with this meter stick. It goes from there to here. It's a length or a distance.
I'm hungry.
Now this is an orange picnic drink, and it takes up 1 liter. It's a volume. It's this big around from here to here. Now this is a second, from now to now. Here's the meter, here's the liter, but where's the second? The second's gone. It's forever in the past. We'll never get it back. We'll never get another chance, another moment to relive that second. Because that second, it's come and gone. Wait, it'll never be back. The second was here, and now it's there. It's gone out off in space-time continuum. We can't get that second back because that's the way time is. See, meters are still here, the liters are still here, but the seconds are coming and going all the time. Time is no picnic. Cuckoo.
Rate 24 hours in a day, determined by the sun's ray. Today the sun will rise. Time, thinking about time makes me feel psychedelicized. Time.
Don't worry, the sun's not moving, the Earth is turning. Time is passing. There's nothing we can do about it. We'll see you next time we cross the meridian.
Produced in association with the National Science Foundation.
Okay, there was a cat. Let me show you. Hold it.
It's always something with you.
This is it. Just like a ball bearing. Okay, this is what I said. It wasn't me. Everybody's excited. Bells and whistles, lights and buzzers. God, no bucket of water. No bucket of water, no head injury. The speed of the truck. The truck. A metronome is very useful to a musician.
Thank you.